Today we're going to discuss inhomogeneities in the universe. And actually, this is the key issue in many respects of the standard cosmological model. So let's start slowly. First of all, what are the perturbations? Of course, we have all kinds of matter in our universe, and also we have gravity. So both energy density of matter, rho, is actually inhomogeneous in the universe. So there is the homogeneous part and also inhomogeneous part, delta rho, which depends on x and time. And also metric is not exactly homogeneous and isotropic, simply in particular because there is perturbations in energy density, and these energy density perturbations produce also metric perturbations via such a Newton's law. So our metric is going to be perturbed. That's the usual notation for perturbations. Let me just write it once. Delta ij is the Kronecker symbol, so that the first terms correspond to homogeneous and isotropic flat constituted symmetric. So that's the extra terms in metric, which are perturbations. Okay. So the primordial perturbations and perturbations until the decoupling of photons or until recombination epoch are very small. Their characteristic amplitude, say delta rho over rho, which is a little bit sloppy because neither delta rho nor metric perturbations are invariant under the coordinate transformations. So one better has to work with either in a certain gauge, which actually I have chosen here. There is no term like dx dt. In principle, there should be, but I have chosen a gauge where this cross term is 0. But either you work in a certain gauge or you work with gauge invariant quantities. But these are technicalities which I'm going to omit. But in any case, the perturbations in everything, in density or in metric, are small, and the characteristic amplitude is a few times 10 to the minus 5. Now, in galaxies, for example, or clusters of galaxies, perturbations are large. They are greater than 1. The overdensity in galaxies is much bigger than 1 in relative terms. However, at early times, they were small. So if you think about early times, then one can use linearized theory to describe perturbations, and the expansion parameter is pretty small. So linearized theory is working very well. That's one thing to understand. Another thing to understand is that we are in linearized theory, so equations for metric perturbations and density perturbations are linear, and our background is homogeneous and isotropic. Since it is homogeneous and isotropic, we can always work in Fourier space, right? So our metric perturbations, h mu, for example, or density perturbations, will be integrals over dk e to I k x h mu of k n times, right? Now, one thing to understand is that this x is, as I discussed yesterday, is a coordinate distance. It's not a physical distance. And therefore, this k, which is conserved quantity, is not a physical momentum. It's not a physical wave number. Rather, it is what's called comoving or conformal wave number. So the physical distance, delta L, is A of t times delta x, and therefore the physical momentum P is k over A of time. And that's precisely redshift, right? The physical momentum gets redshifted because of the expansion of the universe. Now, one more thing to understand about perturbations is that they can be decomposed into different modes. And let me begin by this classification of perturbations by saying that we can think of each mode separately, each momentum mode separately, since momentum is conserved. And for a given mode, of course, three-dimensional rotational invariance is broken, right? There is a direction of momentum singled out. But I have a momentum here, but there is a rotational invariance with respect to in the plane normal to the momentum. Okay, so there is remaining SO2 invariance under rotations around this momentum. Okay? And therefore, we can decompose our perturbations into different modes according to the transformation law against these rotations. Okay? So we have scalar modes. So there are in principle three types of them. One is scalar mode. These are invariant under rotations around the momentum, and these, the components are the density perturbation, for example, the component of metric H naught naught, clearly it's invariant under rotations. Also, as an example, the trace of the spatial part of the metric perturbations is also invariant under rotations, etc. Okay. In terms of helicity, these are helicity 0. Okay. Now, in principle, there could be vector modes. These would have helicity 1, plus or minus 1. And components are rather few. In principle, you can have a velocity of your fluid in the universe. The plasma in the universe can have a certain velocity. And normal components of velocity, normal to the momentum, would be part of helicity plus or minus 1 perturbations. However, if you look into equations for these perturbations, it turns out that these vector modes rapidly decay as the universe expands. So even if they are generated at some early stage, they become irrelevant very, very early, and therefore it's likely that vector modes are irrelevant for cosmology. They decay very fast. And that has to do with angular momentum conservation. As the universe expands, because of the conservation of angular momentum, all components, vector components, the transverse components of velocity decay very fast. Anyway, these are probably irrelevant modes, although there is some literature on vector modes, but it's likely that they are irrelevant. Now, important thing is that one can have also tensor modes which have helicity plus or minus 2.
I'm sorry, could you please explain modes of what it is not yet clear? What?
Well, we are talking about perturbations in energy density and metric, essentially. So we are talking about Fourier modes of metric and density. Okay, and then we can decompose all these perturbations into different kinds. Okay. Now, we have metric here. We have three-dimensional tensor, Hij, and that's the reason why we have also tensor modes, because tensor Hij has, in principle, components of spin 2, right? And that precisely corresponds to helicity plus or minus 2. So these are transverse traceless components of Hij. So that in momentum representation, they are transverse, and they are also traceless, Hii. And you're familiar with them because it's precisely the properties of gravitational waves. Gravitational waves are described by transverse traceless part of the spatial component of the metric. So when you hear about tensor modes, remember that these are essentially gravitational waves. And they are interesting, even though they haven't been observed. Now, of course, scalar modes have been observed. These are density perturbations, and density perturbations are there. Galaxies are formed out of initial density perturbations. Gravitational waves have not been observed, but they are quite interesting, in principle. If observed, that would be Nobel Prize, I think. Now, we have to understand also the behavior of perturbations during the expansion of the universe. Well, in principle, it's a linearized theory. You have Einstein equations, you have one or another kind of matter, and you solve your linearized Einstein equations and equations of motion for matter, and you find the behavior of your perturbations. Let me not go into detail. It's, rather complicated story, although it's a linear theory. But there are several points which I would like to highlight. The first thing is to, well, before doing that, let me discuss radiation domination. We're going to discuss early universe, and in particular, radiation domination stage. The stage which lasted until 80,000 years after the Big Bang. And we are going to discuss the behavior of perturbations at this stage in particular. Now, at this stage, we know that the homogeneous part of the universe obeys the Friedmann equation, which is this. Let me remind you. This is the definition of the Hubble parameter, and it's related to the energy density in the way discussed yesterday. Now, if this is radiation, then its energy density is proportional to 1 over a to the 4. So you can solve this equation easily and find out that the scale factor behaves like square root of t. It's proportional to square root of t. You just plug square root of t to the left and right side and figure out that this is a solution. Now, therefore, the physical momentum written here, or physical frequency, omega, which is the same thing as p, essentially, maybe up to maybe velocity of sound, physical frequency, which is proportional to k over a, behaves like 1 over square root of t, which tells you that the characteristic time, tau, characterizing your perturbations, the time during which the perturbations change considerably, is proportional to square root of cosmic time. Inverse omega is proportional to cosmic square root of cosmic time. And that's interesting because at late times, in the cosmological history, this tau is greater than t. Smaller than the cosmic scale. Which means that perturbations have enough time to oscillate, right, to develop. On the other hand, at early times, the characteristic time of development of your perturbations, this tau, is much greater than cosmic time. The universe expands very fast as compared to the characteristic time of development of your perturbations. Okay? Therefore, the perturbations are effectively time independent. There is no time to develop. Okay? That's peculiarity of cosmological expansion at the radiation domination epoch. Another way to understand this is to think about the spatial scales. Once you know the physical momentum, which is inversely proportional to A, you know the physical wavelength, and the physical wavelength increases like A. So the physical wavelength, let's write it essentially. Lambda of t goes like A t divided by k, modulo 2 pi. Okay? It goes like square root of t. And in the universe, in particular in the radiation domination epoch, you have what is called horizon scale. That's the distance that light travels from the beginning, from the Big Bang. So you imagine you emitted a light ray at the very Big Bang, then it travels finite distance by the time t, and this distance, the horizon scale, is proportional to time. It's not exactly equal to time because of the expansion of the universe, but in radiation domination epoch, you can easily calculate that it's just 2 times t. It travels the physical distance equal to t, and the universe expands. So altogether, the horizon size is 2t at the radiation domination. Okay? So, and this is in the hot scenario, if you think of the Big Bang as the beginning of hot epoch in the evolution, then this is the size of causally connected region in the universe. Now, the thing that I discussed before can be reformulated in terms of these scales, because at early stage, square root of t is greater than t, right? Small t. So lambda is greater than the horizon scale. So the picture is quite unusual. You have big, relatively big, domains in the universe, over which your universe actually looks like homogeneous universe. If you think of a given mode, then it's bigger in size as compared to the causally connected region. So that any observer that would sit there would think that his universe or her universe is homogeneous, even though the entire big universe, stretching out over many, many horizon sizes, is inhomogeneous. So your inhomogeneities are large compared to the visible universe of them. So these are kind of independent universes in these patches of the size comparable to the horizon size. Okay. Now,
sorry.
Yes.
You tell time should be small, but compared to what scale small?
Well, you have to compare the physical momentum k over a, and a is square root of time, proportional square root of time. You have to compare it to the Hubble parameter. That's the physical terms. Okay. So at early times, this momentum is much higher than the Hubble parameter. Yeah.
You say this for all k, where the below k and possible value of k large absolute.
Sorry?
Can you not say this? How can you say this for all k, all values of k?
Well, for a given value of k, the sequence of events is this. The perturbation starts off as big super horizon, and then it enters the horizon. The time at which it enters the horizon depends on k. The larger momentum, the shorter wavelength, the earlier it enters the horizon. But this sequence of events works for each value of k. Okay? Right. So now the question is, will perturbations ever superhorizon? We know that there are perturbations, but we can ask if this situation, strange situation where you have your perturbations much bigger than the horizon size, was it ever realized? Maybe it happened that the perturbations were generated later when the corresponding wavelengths are already smaller than the horizon size. That's an interesting question and very deep question. Let me give you the answer. The answer, experimental, derivational answer, is yes. They were. Okay? That poses important question. Because how could that be that your inhomogeneities in the universe started off much bigger than the causally connected, the size of causally connected region? How could that happen? That obviously contradicts causality. Right? How can you generate anything? How can you get anything bigger than the size of your causally connected domain? Obviously, this is in conflict with causality. Right? So that tells you, as I told you in the beginning, that tells you that there must be some earlier stage at which the evolution was completely different from this power law behavior, square root of t. And at this stage, the behavior of perturbations should have been completely different from their behavior at the radiation domination point. And that's precisely what inflation is about. It's real strength of inflation is that it solves this conflict, solves this problem with super horizon perturbations, super horizon physics.
I'm sorry again.
Yes?
Well, maybe it is possible to solve this problem by saying that there were only high momentum.
No, we know that the perturbations are of all possible momenta, galactic scales, clusters of galaxies, and we actually know that even at much bigger scales, there are perturbations. This is experimental fact.
Well, just if you imagine that it was just a huge bang, and okay, everything has big momenta, and then this condition is.
No, we know the perturbations. We know that there are perturbations of all possible scales, and perturbations of galaxy size re-enter the horizon at about a few keV temperature. So we're talking about pretty late universe. Before 1 keV temperature, which would correspond to, let's see, 1,000 seconds or so after the Big Bang, pretty late, we know for sure that these temperatures were realized in the universe. Before that, the perturbations of galactic size were super horizon. So it's not a joke. It's not, anything we can only guess about. We know that perturbations that form galaxies were bigger than the horizon size at temperatures of about 1 keV, and we are sure that the universe had temperatures of about 1 MeV definitely. So one cannot, hypothesize here. Okay, let me begin with inflation, therefore. Let me tell you that inflation, what it does, basically, it is basically the epoch at which the scale factor goes almost exponential. It's equal to e to the ht, where h is a constant. It's a Hubble parameter, but it's a Hubble parameter at inflation. H is almost a constant. It slowly changes in time, but very slowly. And then the story is different. The story about the sizes of perturbations as compared to the Hubble size, the story is different. Let's look at this k over a. A goes exponential. Hubble parameter stays constant. So early at inflation, k over a is much bigger than h. Yes, sorry. Early at the radiation domination is small. So now at the radiation domination, the momentum is small compared to the Hubble scale, and the characteristic length is bigger than the Hubble length. At inflation, the situation is inverse. Early on, the momentum is high because A is small, and the physical momentum is greater than the Hubble scale. Physical wavelength is shorter than the Hubble length. And only later, perturbations enter the horizon. Later, the momentum scale is less than the Hubble scale. So the situation of inflation is reversed compared to radiation domination. So if there was inflation, then the picture is this. This is time here on the horizontal axis, and here are two characteristic parameters. One is the Hubble scale. It remains almost constant, slowly decreasing during inflation. And this is the physical momentum, Q, the same thing as P. The physical momentum, K over A. At inflationary epoch, it's high in the beginning, so my perturbations are inside the horizon. Everything is well from the point is good from the point of view of causality. They are small, and their characteristic time scale is small compared to the Hubble time. Then they enter the horizon here, exit the horizon here, stay outside the horizon, stay larger than the horizon size for a long time, and then get out of the horizon at radiation domination or meta-domination. That's what inflation is about. Gives you causal mechanism, at least possibility of having causal mechanism for generating density perturbations. Okay. Success of inflation is that it actually generates automatically density perturbations in our universe. I will talk about that later, but let me tell you that that's not the only possibility one can think about. And it's not yet established that inflation was really the beginning of the cosmological evolution. Let me warn you that very often people take inflation for granted and include inflation into standard cosmological model, but that's not guaranteed yet. It's not established yet. For example, one can think of a different possibility that the universe starts out big, then it shrinks, so one has contraction in the beginning rather than expansion. Then, by some miracle, the situation changes, contraction stops, and the expansion begins, and our conventional hot Big Bang epoch begins. In that case, you can always also have causal structure different from the hot Big Bang scenario. So this is my time here. In that case, the Hubble parameter is small, the universe is large and almost empty. So the Hubble parameter is small, the universe contracts, small and negative. The universe contracts. Then by some miracle, the Hubble parameter, this is the Hubble parameter. The Hubble parameter increases, becomes positive, the universe starts to expand, and here is the radiation domination. One can think of this possibility. Then obviously, because the Hubble parameter is very small early on, you can have perturbations inside the horizon initially, which then cross the horizon in. So this is the modulus of the Hubble parameter. So this is the momentum, the physical momentum, P equal to K over M. Okay? So they re-enter the horizon, sorry, they go up here, down here. They exit the horizon at late stage at contraction, and then they enter the horizon at the radiation domination stage. That's another option. Well, there is even more weird thing, that the universe starts out almost Minkowskian. So this is called bouncing universe scenario. This contraction and then expansion is called bouncing universe. And there is another possibility which is called genesis. People were brave to call their scenario genesis. Right? Remember Bible? Genesis. So genesis is a scenario in which you have, again this is time, Hubble parameter which is nearly zero, then it increases further, and then decreases again back to radiation domination epoch. So this is genesis epoch, and this is radiation domination. Okay? Again, my physical momentum is bigger than the Hubble parameter. Then it decreases slowly, and re-enters the horizon at radiation domination. Until recently, these kinds of possibilities were unthinkable because, for example, in this case, since my Hubble parameter increases, you recall the Friedman equation here, and understand that energy density should increase. That's something pretty weird. The universe expands, and yet the energy density in it increases rather than decreases. And the theories in which this can happen were unknown until very recently. Today, there are several models, field theoretic models, which realize this possibility without any problem. So it is conceivable that such a scenario could be realized in the universe, provided that you have pretty strange matter, strange fields, but who knows what fields were there in the beginning of the universe. Okay, so that's to warn you that inflation is not the only option. There are other alternatives which may not look as natural, as nice as inflation, but yet nobody knows still what scenario was actually realized in the universe. There's not enough observational data yet. Now, coming back to inflation, how do you generate, first of all, how do you get this exponential behavior? And second of all, how do you generate perturbations of inflation? Now, inflation, in its simplest version, is based on a scalar field, which is called inflaton, new scalar field, typically, although people discuss Higgs inflation as well. But in the simplest version, inflation is based on the field called inflaton, with the usual action, the standard conventional action for the usual action for the scalar field, integral before x, square root of minus g to have the volume element invariant under coordinate transformations, and then you have g mu nu, g mu phi, minus v of phi. I'm not going to go into much detail, but let me write a couple of formulae. Now, one assumes that the field is homogeneous. It depends on time only. It's homogeneous in space. And then this action becomes very simple. Let's come back to a homogeneous universe. Square root of g is the determinant of the metric, and therefore you get d3x time. Square root of g is a cube. Here I have a half of phi dot squared minus v. Okay, if I neglect special derivatives. And from that, you can easily obtain an equation for this inflaton field phi. And this equation is simple. You just vary this action with respect to phi, and you get phi dot dot plus 3 a dot over a h times phi dot equals to minus d over d. So it's similar to the, second Newton's law of mechanics, except that you have a friction term here. And this friction term does the job of to produce exponential expansion of the universe. Namely, if the Hubble parameter is large, then this friction term is big. That means that phi moves very slowly along its potential. And you can work out the conditions for that and figure out that in the usual cases with usual potentials, power law potentials, this happens if the value of your field is large. That's the only thing that's necessary. Okay? So the inflationary picture is this. Once your field is large out here, then the field stays constant. It produces large energy. The potential is large. The energy density is large. The Hall parameter is large, and the Hall friction prevents the field to roll fast along the potential. So it stays constant here, slowly moves down, then it moves faster. In the end, it starts to oscillate. This inflationary stage finishes, and these coherent oscillations of the field produce reheating of the universe. You know that once you have time-dependent fields, then they tend to produce particles for you, and it's clear that these inflaton oscillations will eventually be converted into particles. So that's the inflationary state. Okay? Right.
Sorry, but what are the initial conditions?
The initial conditions is that in a patch of the universe comparable to the Hubble size, the scalar field is large and nearly homogeneous. That's the only thing that's necessary. Okay. The energy density may be well below the Planck density, or it may be a quarter of the Planck density. And then inflation automatically begins. So an assumption is that in some patch of the universe, which is small, it could be even Planck size region, accidentally the scalar field is homogeneous and large over the entire patch. That could be a fluctuation. Now, how do we produce perturbations? The origin of perturbations in this case are, and probably this is the origin of perturbations no matter what scenario you consider. The origin of perturbations are vacuum fluctuations of your fields, in particular in this case of the inflaton field. So let me briefly discuss vacuum fluctuations in Minkowski space. Interesting, right? We are talking about vacuum fluctuations which eventually produce galaxies. Now that's probably very likely the real origin of galaxies. Which is vacuum. Now let's discuss briefly vacuum fluctuations in Minkowski space. In the beginning, in slightly unusual terms. So let's discuss free quantum fields. In the inflationary scenario, this is the inflaton field, which is because at the inflationary stage it's essentially free. It's non-interactive, very little. And the point is that vacuum fluctuations viewed as random field are actually the same thing as Gaussian random field. So by definition, Gaussian random field is the field whose correlation function, so we are talking about random fields. The things that characterize random fields are correlation functions, and the correlation functions for Gaussian random field, and that's Gaussian, obey weak theorem. Okay. So Gauss, when discussing Gaussian random variables and Gaussian random fields, didn't know about weak theorem. But in the language of quantum field theory, the definition of Mr. Gauss is that this is the field that obeys Weik's theorem. And that has to do with the fact that probability distributions is Gaussian. It's e to the minus variable squared. And the wave function of harmonic oscillator has the same form, e to the minus q squared, right? And quantum field is a collection of oscillators. So that's the relationship. And sure enough, the correlation functions of free quantum fields obey Wick's theorem, right? That's we learned from our field theory courses. So free field in the vacuum state is Gaussian random field. Now, another point is that the development in time of Gaussian random field, if it's a linear development, does not change its nature. The correlation function may change, but the Wick theorem remains intact. So if you think of linear field, whatever its evolution is, if it's a Gaussian random field, it will remain Gaussian random field. Now, for Gaussian random field, everything is determined by its correlation function, one single two-point function, correlation function. And if the correlation function, say phi of x, phi of y, I'm talking about equal time correlator. If this correlation function is a function of the difference, x minus y, independent on the direction of the direction, so that's called homogeneous and isotropic Gaussian field. Its correlation function is isotropic and homogeneous. It depends only on the difference. Then everything is determined by the Fourier expansion of this, of Fourier components of this function, of this correlation function. All correlation functions are determined by this f of k, and f of k is a function of the modulus of the momentum. Or, in other words, one can introduce what's called power spectrum, namely, and there is one-to-one correspondence between these two. Namely, one can think of the fluctuation at a given point in space, of course, is proportional to the integral of this f of k over momentum, but one can think of it as an integral over the modulus of momentum, and here is p of k. And this is power spectrum. So this is called power spectrum, and that's precisely the quantity that I wrote for you in the very beginning of this lecture. Power spectrum. Now let's calculate power spectrum for quantum field, quantum scalar field massless in Minkowskian space. So we know that this field phi of x at a given moment of time equals to integral e3k 2 pi cube square root of 2k e to the I x, say at time equals 0, creation operator a of k plus e to minus I k x, annihilation operator a k minus. And these obey the usual commutation relation a okay. This is the reminder how the free quantum field is decomposed into the creation and annihilation operators. And therefore, you can immediately calculate phi squared over vacuum. This is vacuum expectation value, and that's important that this is vacuum. Only in vacuum you have Wick theory. Now what you have to do, you have to multiply this thing on the same phi of x, and then take the average. What will happen is that this a minus will go through a plus in the second field, there will be a delta function, and that's it. So what you're going to get is the integral of G3k 2 pi cube 2k, right? So let me write it in this fashion, introducing power spectrum, and we get integral. G3k will give me k squared dk, so this will be k squared over 2 pi cube dk also. And here is the power spectrum, k squared, for the free scalar field in Minkowskian space. Okay, it's blue. Its value grows with momentum as k squared. Okay? Now how inflation works. Inflation works rather simply. Again, we know that at early time, now I'm talking about perturbations of inflationary field. Okay? Not the homogeneous part, but perturbations about the solutions of a given moment. So this inflaton field, the perturbation of the inflaton field, remain inside the horizon. They oscillate like, and inside the horizon, the time scale is much shorter for the perturbations than the Hubble time. So the universe expands very slowly for this perturbation. So it behaves nearly as in Minkowskian space. Just redshifts. The momentum gets redshifted and that's it. So the amplitude, let me introduce the amplitude. The amplitude of the perturbation here, this is square root of t, and for free field Minkowski space it's k over pi. Or rather, physical momentum p over pi. Okay? So the amplitude of the perturbation gets redshifted. Delta at inflation of p goes like p over 2 pi. And now, since I'm in the expanding universe, my momentum gets redshifted. Amplitude decreases by p until horizon exit, until p, physical momentum, is bigger, becomes a quarter of the Hubble scale. Okay? And then it stays constant. Because the universe is smaller, the Hubble size is smaller, there is no time to develop, so it stays constant. Delta of t stays constant afterwards. So you immediately get that once the perturbations exit the horizon, their amplitude stays constant and equal to h over 2 pi. And that's the exact result. Indeed, for massive scalar fields, or effectively massive free scalar fields in inflationary universe, their superhorizon modes, the modes which exit the horizon, they have this amplitude. And this is a large amplitude because Hubble parameter can be very large in inflation. So even though the wavelength increases, normally that would mean that the amplitude decreases, but that's not what happens in inflation. Inflation, you get frozen again. And that's the origin of perturbations. That's it. That's the whole story. It can be much more sophisticated, but that's the mechanism. And of course, they have to be reprocessed into density perturbations. These are amplitudes of perturbation of the inflaton field itself. But you understand that if you have perturbations in the inflaton field, then you get also perturbations in energy density, because perturbations in the inflaton field mean that somewhere in the universe your field is bigger than on average, somewhere it's smaller, and therefore the energy density here is different in different parts of the universe. So you have to reprocess, they are automatically reprocessed into the density perturbations. There is an extra factor that enters the density perturbations, delta, what's called zeta. There is some extra factor which is model dependent, but it is proportional to the. So this number is actually depends on the model, depends on the potential in particular. So, and that's the important thing. The important thing is that for different inflaton potentials, you have different values of the Hubble parameter and also different reprocessing factors, which I will not write explicitly. Okay? So that's how you generate perturbations at inflation. And a few comments before I finish this lecture. A few comments. One comment is that, first of all, the amplitude here depends on the parameters in the potential, right? If you have large energies, you have large Hubble parameter, you have larger amplitude. Now, you get correct amplitude for density perturbations. Correct meaning we know what they are. They are a few times 10 to the minus 5. And that's precisely what we need here. That's the number you want to obtain. For that, you have to dial parameters in the potential. For example, if we have lambda phi to the 4, you have to dial lambda equal to 10 to the minus 13. Which is not very natural. That's one of the problems with inflation, that you have to dial parameters in the potential in rather weird way to get the right amplitude for density perturbation. That's almost square of the 10 to the minus 5. There are extra factors due to this reprocessing factor, so altogether get the 10 to the minus 13. Then, but if you allow yourself to have scalar field with these rather contrived parameters, then you get correct amplitude. Second point is that you have nearly flat spectrum. Look, this is almost constant. Hubble parameter at inflation changes very slowly. It's almost constant in momentum space because, as I told you, the different modes, different momenta exit the horizon at different times. The longer the mode, the earlier it exits the horizon at inflation. So the Hubble parameter depends on time weakly, and therefore you get weak momentum dependence. So my power spectrum, P theta, which is the same thing as delta squared, is almost scale independent, right? But not quite. So inflation predicts nearly flat power spectrum, but not quite flat. And that's because modes of different momenta exit the horizon at different times, and at that time, the Hubble parameter and other factors are different. So, in terms of our spectral index of yesterday, this means that the spectral index is not going to be exactly 1, but it must be close to 1. That's the characteristic prediction of inflation. Remember our definition that this power spectrum is A scalar amplitude times K over some conditional K star, ns minus 1. So this ns must be close to 1. Okay? But not exactly equal to 1. Again, this is model dependent. The value of ns depends on the choice of your inflaton potential. Another point is Gaussianity. Gaussianity must be excellent here. I noticed that the potential must be very flat. The self-coupling, for example, must be very small to generate the amplitude of right order. The the self-coupling must be small. So we are dealing with really very, very weakly interacting fields. And free fields obey Gaussianity, so perturbations must be Gaussian. So the simplest inflationary models predict that the Gaussianity must be excellent. Now, another point is that not only scalar fields get perturbations during inflation, but also all kinds of fields, right? In particular, gravitational fields. Gravitons are as good particles as inflatons. So one has tensor perturbations, whose power spectrum, so we are talking about gravity waves, the power spectrum will be again h over 2 pi squared. And then there is some, conversion coefficient, which involves the gravitational constant or Planck mass, 16 over 10 squared. This is dimensionless quantity, and that corresponds to the fact that we are talking about metric perturbations, which are dimensionless. And again, compare these two things, or square of this and this, and you see that they are nearly of the same order of magnitude. Modulo this conversion factor, they are the same in Planck units. So you predict pretty large amplitude of tensor perturbations. So what's the situation? The situation, let me finish with this. This is the situation with measurements. On the right side, on the horizontal axis, this is the NS, this quantity, the scalar the scalar spectral index, and on the vertical axis, we have ratio of the tensor to scalar power spectrum. Okay. These are allowed regions. First of all, you see that the scalar spectral index is not exactly equal to 1. It looks like. These are 1 and 2 sigma contours. Second, these are the predictions of different inflationary models with quartic potential there. Here, there is some uncertainty which I'm not going to discuss, but that's the uncertainty here. That's the prediction of the potential m squared phi squared beta. Here is the prediction for linear potential, whatever that could mean. And this is prediction of the first Starobinsky's model of inflation. The very first model of inflation was invented by Starobinsky. It was based on modified gravity, mass squared gravity. So the situation today is rather, intriguing. First of all, no gravitational waves have been observed yet, only limits. Second, scalar tilt seems to be, scalar spectrum index seems to be smaller than 1. The spectrum looks like somewhat red. And it looks like the original conjecture by Harrison and Zelgovich, this is this pink square, saying that the spectrum must be exactly flat and no gravity waves. It looks like this point is disfavored. This is the result of rather complicated fitting to the cosmological data, most important part being CMB data. I will talk about CMB tomorrow. But that's the situation here. Of course, we look forward for Planck, because Planck will be much better in this figure than current CMB data from WMAP. And I think within a year, we will know whether there are gravitational waves, if they are as large as predicted by simplest inflationary models. And we will also know for sure whether the scalar spectral index is different from Harrison-Zelgovich value 1, whether the spectrum is not exactly flat. That will be interesting because inflationary scenarios give these predictions in this ballpark, and we are approaching this ballpark with cosmological observations. All right, let me stop here. Tomorrow we're going to discuss CME data, what do they tell us, and what we can expect from future CME. Thank you.
Questions, please?
Can it be that when we choose the initial value of inflaton field, it's the potential will be more than mass of Planck mass to the fourth power?
Well, it's hard to tell because we don't know what happens at energy densities comparable to Planck energy density, Planck to the fourth. So we don't have any clue on physics. Probably physics is quite different from this classical, essentially, classical physics we are thinking about when talking about inflation. So people try to avoid going to super Planckian energy densities. And indeed, with so small value of coupling constant, you don't need to have very large value of the inflaton field to have inflation. The energy density could be a lot smaller than, because of this factor lambda, the field itself might be large, it is required to be large for inflation, but lambda is so small that altogether this energy density is well below the Planck energy density. So whatever happens at high, in other words, whatever happens at high energy densities, if you get into this regime where your field is large but energy density is small, you can trust your field theory. You do not worry about huge quantum gravity effects. So all this picture is valid.
Is it more natural to start from some formalized field T rather than having some PC?
Not really. You can think of, again, coming to this Planckian physics. Suppose somehow there is, at Planck energy scale, you have very wild behavior. The field fluctuates, the metric fluctuates, everything fluctuates in rather unpredictable way. But if there is a fluctuation that has this property that the scalar field is large but not exceedingly large there, and homogeneous over over the region which is somewhat bigger than the Planck region, not many orders of magnitude bigger, but say 5–10 times bigger in size. Once this fluctuation occurs, then inflation immediately starts in this patch. This patch exponentially expands, and we get to this inflationary picture. So if you allow for fluctuations of all kinds, somewhere in the universe you will have conditions which guarantee that inflation starts.
More questions?
Okay. You can compare what the difference from the horizon in a cosmological and horizon in a gravitational collapsing body, collapsing system.
There are similarities, but well, there are similarities, but not direct, one-to-one correspondence.
More questions? I have a question.
Yes.
At the present day, the best fit value for the spectral index is about 0.95, 96.
Yeah, that's what it's there. It's, oops. Well, it's about 0.95. Assuming that there are no gravitational waves, the best fit is 0.95.
So, if there are no more questions, let's thank our speaker once again.